Okay, as we start Unit 2 derivative applications, we're going to start with instantaneous rate of change. I'm going to go through 6 examples in the lab manual. The objective is on page 32 in the lab manual, number 20, given a function, be able to find the instantaneous rate of change at a given point and interpret the meaning. So the IRC stands for instantaneous rate of change. The IRC is the rate at which the function is increasing or decreasing at a certain level, at an instant, at one point. We've done ARC, that's between 2 points, but now the IRC is at 1 point. The IRC, when you're asked to find the IRC, that's finding the derivative of the function evaluated at 1 point, at that value. And the units are really important. The IRC units are just like the ARC units. It's always whatever the Y unit is per one additional X unit. Y unit per one X unit. So if you want to make a general template, you could say at X, at the point X, the function, whatever the function is either increasing or decreasing at a rate of whatever your derivative value you find is 1 unit Y units per one additional X unit. So if we do just an easy example without Excel or anything, if I have the cost of manufacturing an item is C of X equals 4.5 X squared plus 6, and X is the number of items and C is the cost in dollars, then my X is number of items and my Y is cost in dollars. How quickly is the cost changing when 10 items are produced? That's a key word there, quickly. If you are asked how quickly, you are looking for an instantaneous rate of change because it says when exactly 10 items are produced. So how quickly is the cost changing means find the IRC. The IRC is the derivative. Okay, so the derivative is 4.5x squared is 9x. Then I want to evaluate at 10. So C prime of 10 means 9 times 10, so that's 90. Now look at the units. The IRC units are always Y value. Y is dollars per X, which is items. So the C prime of 10 is $90 per item. That's the units. Finally, to interpret this, you would say there's the point 10. When X is 10, when 10 items are manufactured. The name of the function is, this is a cost function. The cost is, since this is positive, it's increasing at a rate of 90 Y units, $90 per additional X unit, per additional item. At 10 items manufactured, the cost is increasing at a rate of $90 per additional item. That's how you interpret. So as we begin this, what you're going to have to do is go back and forth between paper and Excel. Write your Math English Dictionary. Write down what independent variable units are and what the dependent variable units are. Then you're going to take the derivative on paper. Don't try to take the derivative and type it in at the same time. That's nearly impossible to be 100% accurate on that. Then you're going to take the derivative that you wrote on paper and you're going to type it into Excel. You'll see me go over this, but I try to never use the quotient rule because it's really hard to type in because of the amount of parentheses. So most of the time people don't do what I've got written here. What I suggest you do is use the chain rule. So you can take anything that's in the denominator and put it in the numerator if you use a negative exponent. So you'll see me do that. Or you could do what I've written here. You can split the derivative up and type a numerator in a column and a denominator in a column and then divide in a third column. But most of the time people don't do that. Okay, so this is number 1 in your lab manual. It says the function s of x equals 100,000 plus 400,000 times the natural log of x expresses the relationship between sales of a product in thousands of dollars, and the advertising for the product where X is thousands of dollars spent on advertising. So the first thing that I should do is write down what the X and Y stand for, the input, the output stand for. And so that's what I did right here is I said, all right, well, let's let X equal the money spent on ads, and that's in thousands of dollars. And then the output S is sales of the product, also in thousands of dollars. So they're both units money and they're both times 1,000. Now the next thing I want to do is I want to understand that instantaneous rate of change is a derivative. And so I said IRC is equal to the derivative of S of X, and so my function over here, the derivative of 100,000 is 0, and the derivative of 400,000 times natural log of X, well, if you think of it this way, this is a constant, 400,000 comes down, and the derivative of natural log of X is 1 over X. So constants get to come down. And then that is simply 400,000 over 1 times 1 over X. So the derivative is 400,000 over X. So you have to do that on paper. And then B says find S of 10 and explain its meaning. So that tells me that I want to use the original function. I have two things. I have the derivative, the instantaneous rate of change, and I have the original function, which gives us relationship between ads and sales. Now this is asking us to use the original function, so I'm going to plug 10 in, and that would be 100,000 plus 400,000 times natural log of 10. I'm going to leave that and use Excel to find that value, and then I'll interpret it. And then C says find S prime of 10, so that's using the instantaneous rate of change derivative. So I'm going to plug 10 in, so that would be S prime of 10 equals 400,000 divided by 10, and I don't need Excel for that, so I'll keep going. That is S prime of 10 equals 40,000. But remember, we're in thousands on both of these, so it's time to interpret. So the way you interpret IRC is you say at this value right here. That's your input at 10, but you got to turn it into English. So this is times 1,000, so 10 times 1,000 is 10,000. It's money spent on ads. That's what X is. So at $10,000 spent on ads, this function is about sales. The sales is increasing since it's positive at a rate of, this is what it's increasing at, but this is in thousands again. See? So 40,000 times 1,000 is 40 million. So it's increasing at a rate of $40 million per $1,000 spent on ads. And you may be wondering, can I divide this into this and make it simpler? Yes, you can. An alternate answer would be it's increasing at a rate of $40,000 per $1 spent on ad. You can divide that and simplify. So I would accept either answer. Okay, so for number 1, I have my original function, and it is giving me, when I know X, the money spent on ads, times 1,000, then I'll know the sales times 1,000. And I also have my derivative, which gives me my instantaneous rate of change. So question B, I need to use the original function, and in question C I have to use the derivative. So when I'm typing this in, I'm going to let X be my column A, my input, and then I'm going to type my original function next, and then I'm going to type my derivative next. And this one you're only evaluating one value, which is 10. And I'll put my original function in, so that would be equals 100,000 plus 400,000 times ln parentheses cell A2. And then my derivative is 400,000 divided by A2. So now I have my calculations, and so to explain its meaning, I'm going to go over here to the key, and you would want to go ahead and write it in your lab manual. So let's go to the key, and let's make sure I have the same answers. Okay, and so here B, S of 10 equals, let's put some commas in here, 1,021,034. But X is in thousands, and X stands for spent on advertising. So when $10,000 is spent on ads, then the sales are not just 1 million, but multiply this by 1,000 and add 3 zeros on the end. Or you can just use Excel, just click on this cell times 1,000, and you get this number, $1,021,034,000 in sales. And then in question C, S prime of 10 is an instantaneous rate of change. There's your value. So it's in thousands, so we'll multiply this by 1,000. And it's a very large number. There it is. And so the way you interpret an instantaneous rate of change again, at $10,000 spent on ads, the sales are increasing at a rate of this value here, $40 million per 10,000 spent on ads. So, and that actually should be 1,000 spent on ads. And so then if you divide that out, that's 40,000 per $1. And it should be 1,000 because it's usually per one additional dollar spent on ads, but it's in thousands. So that's in 1,000. And then if you divide 40 million by 1,000, you just take 3 zeros off. You get $40,000 per $1 spent on ads. Okay, IRC number 2 says the model below measures the percent of the normal level of oxygen in a pond where T is the time in weeks. So T is our input, and it's time, and the units are weeks, after organic waste is dumped into the pond. So this model represents the percent of normal level of oxygen. So the units is our percent. First question A says, what will be the percent of the normal oxygen level after 1 week? So we have this model, which gives us a relationship between, if you know the number of weeks, you'll know the percent normal oxygen level. So this question is asking us to use the original model. The next question says how quickly is. How quickly is a rate of change? How quickly is the percent of the normal oxygen level changing after 1 week? So we are wanting to know an IRC, an instantaneous rate of change, and so that means we're going to need to take the derivative of this function. So we'll do that, and then we'll go to Excel and talk about which one of these we should use. So the derivative of this function, this is a quotient, and you can't divide out this binomial. You're stuck with it. You could move this up into the numerator and use the chain rule, or you could use the quotient rule. And I'm one who really doesn't like to use the quotient rule very often, so I am going to rewrite this. I don't like typing in the quotient rule into Excel. So this is equivalent to t squared minus t plus 1 times t squared plus 1 to the negative 1. So now I'm going to use the product rule, and when I get to needing to take the derivative of this one, I'm going to have to use the chain rule. So the product rule is first times the derivative of the second plus the second times the derivative of the first. So it's time to take this derivative. So the derivative would be the first, which is t squared minus t plus 1. That's the first. Times the derivative of the second, and as I said, the second is going to involve the chain rule. So the chain rule says that you bring the exponent to the front and then leave the inside unchanged and reduce this exponent by 1, so that's negative 2. So that's the derivative of what we call the outside times the derivative of the inside. The derivative of t squared is 2t, and the derivative of 1 is 0. So all of that is the derivative of the second, and then first times derivative of second plus the second, t squared plus 1 to the negative 1, times the derivative of the first, which is going to be 2t minus 1. So this is my derivative. Okay, now I'm going to stop and we'll type this in and we'll be able to answer all these questions. Okay, question 2, we've already taken the derivative. In question A, we want to know the percent of normal oxygen level after 1 week. So that's asking you to just demonstrate the relationship. If you know the week, you'll know the percent normal oxygen level. So this would you would use the original. And then question B, how quickly is the percent changing? That's asking for the IRC. So you would use the derivative. And then, so we already know we're going to be going back and forth between the original function and the derivative. So let's type that in. So t is my input time in weeks. And then O of t is my original function. Gives us a relationship between weeks and percent of normal oxygen level. And then O prime of t is the derivative, the instantaneous rate of change. Okay, so question A, after 1 week, so my input is 1, and then I would type my original function. Now I have to make sure I use parentheses, which I've already written in here for you. This little horizontal division is a grouping symbol. So parentheses t squared minus 1 times t plus 1, close the parentheses, that's my numerator, divided by parentheses t squared plus 1, close parentheses, that's my denominator. My derivative is right down here. It's very long. Parentheses t squared minus 1 times t plus 1, close the parentheses, times parentheses negative 1, close the parentheses, times parentheses t squared plus 1, close the parentheses, caret negative 2 times parentheses 2 times t plus parentheses t squared plus 1, close the parentheses, caret negative 1 times parentheses 2 times t minus 1. So every time I've said t, I've been clicking on cell A2. Before I hit enter, I'm just going to check it. Okay, and that looks good, so I'm going to hit enter. Alright, so now the percent normal oxygen level after 1 week would be this original function here. And then how quickly is it changing after 1 week? That would be this value here. And then percent of normal oxygen level after 5 weeks, I'll put 5 in here. And that's going to be not the IRC. This is just asking for, if you know the weeks, what's the percent normal oxygen level. So that's right here. and then compute the rate of change of the percent of normal oxygen level after 5 weeks and 8 weeks. So let's put in 8, and we want to compare these two IRCs. So this one and this one. Okay, so we have those values. I'm going to go over here and look at the key and talk about these. Okay, so the first one, the interpretation would be after 1 week. It's like an if-then. It's just the original function. If I know T, then I know O. So after 1 week, the percent of normal oxygen level is 50%. Question B, how quickly is it changing after 1 week? We found that that was 0. So the way you interpret it, an IRC interpretation would be after 1 week, at that point, the percent of normal oxygen level is changing at a rate of 0% per week, which really you could just go ahead and say it's not changing. And then after 5 weeks, you have what is the normal level of percent of normal oxygen. That's this right here. And that turned to a percentage is 81.8%, or 81%. After 5 weeks, the percent of normal oxygen level will be 81%. This is not a rate of change. This is an if-then. If I know the number of weeks, then I know the percent normal oxygen level. All right, and then the last one, we want to compare these two rates. So the IRC at 5 is this one, and the IRC at 8 is this one. So I have O prime of 5 is 0.036, and O prime of 8 is 0.015. Okay, and so the IRC interpretation, you would say at 5 weeks, that's the instantaneous part. The name of the function is percent of normal oxygen level is, it's an instantaneous rate of change, so the word increasing, at a rate of, the value is 3.6% per week. So the units are always Y units per additional X unit, so 3.6% per week. And at 8 weeks, the percent of normal oxygen level is increasing at a rate of 1.5% per week. Okay, what the derivative tells us is this: the percent of normal oxygen level from 5 weeks to 8 weeks is increasing at a decreasing rate. So if you look here, this value here is 80%, and this value is 87%. So the actual function is showing that it's increasing, but the rate is decreasing. So the original function is showing that there's an increase in percentage rate. The derivative is showing that the rate is slowing down. So this is increasing because the numbers are getting bigger, the percents are getting bigger, at a decreasing rate because the rates are slowing down. Okay, so number 3 says a population of bacteria is introduced into a culture. The number of bacteria P can be modeled by P of T equals 500, parentheses 1 plus 4T over 50 plus T squared, where T is time in hours. Since the bacteria was introduced, and P, the output, is number of bacteria. And we want to find the rate of change of the population after 2 hours. So we are going to need to take the derivative of this function, and there's a variety of ways you could do it. I'm going to go ahead and just simplify this. So I'm going to multiply this 500 into that binomial. So that would be 500 plus 500 times 4 is 2000 T over 50 plus T squared. And then I'm going to rewrite this as 500 plus 2000t times 50 plus t squared to the negative 1. And now I'm going to take the derivative. So the derivative of 500 is 0. And now I can use the product rule on this. So that would be first times the derivative of the second, which you would have to use the chain rule. So that's negative 1 times 50 plus t squared to the negative 2. And then the derivative of the inside is 2t. So this would be first times the derivative of the second plus the second, which is 50 plus t squared to the negative 1, times the derivative of the first, which is 2000. And then we'll check it. So we have 500, that derivative is 0. The first times the derivative of the second, negative 1 times this parentheses unchanged to the negative 2 times the derivative of the inside 2t. So that's the derivative of the second plus the second times the derivative of the first. Okay, so number 3, we just want to type in the derivative. So t is time in hours, and p prime of t is right here, and I cut it off accidentally, so I'll help you out when it comes to the end there. But we want to find the instantaneous rate of change at 2 hours. So I went ahead and put the 2 in, and I'm going to put this derivative in. So that's equals parentheses 2000 times a2, close parentheses, times negative 1 times parentheses 50 plus a2 squared caret negative 2 times 2 times a2. Okay, plus, and then towards the end there it's 50 plus t squared, and that is to the negative 1, times the derivative of the inside, the derivative of the first one, which would be 2000. And before I hit enter, let me just check that. So this is, notice I don't have to have parentheses around everything, even though I've wrote parentheses here. Okay, and that looks good. And so I get this value. Okay, so and again, to interpret, let me click it over to the key where I've got it written out. Okay, so this value is my instantaneous rate of change right here. And the way you interpret it, you're finding at 2 hours. So at 2 hours, P stands for number of bacteria. So the number of bacteria is, it's positive, so it's increasing at a rate of 31.55 Y units. We're talking about bacteria per hour. So if we use this Math English Dictionary, then you can see what the units are going to be. Instantaneous rate of change, ARC, is always Y units per X unit, bacteria per hour. So that's how you interpret that one. Number 4 says the cost of fuel consumption in operating a yacht is given by the function C of S equals 3S squared plus 1200 over S, where S is the speed of the yacht in knots. My input variable is S, and its speed, and the units are knots. And then C is cost, so that's dollars, of fuel. Then it says find dC over ds. That's the derivative of the cost function with respect to s when s is 10, and interpret the results. So again, we want to find the derivative. So this is a monomial, and so the easiest way to take this derivative would be not to use the quotient rule and not even to use negative exponents, but to just divide this s into both these terms here. So that would be C of S is equal to 3S squared over S plus 1200 over S. which is c of s is equal to 3s, because s squared divided by s to the 1 is just s to the 1. You subtract. And then I'm going to rewrite this as 1200 s to the negative 1, so I can use the power rule on it. So we have not yet taken the derivative, but now I can take the derivative using the power rule. So the derivative would be the derivative of 3s is 3, and the derivative of 1200 s to the negative 1 would be negative 1200, since you multiply 1200 times negative 1, and then s to the negative 2, since you reduce the exponent by 1. So now I have a derivative, and I have an original. You can use this or this as your original, but it says that we want to find the derivative when s is 10. So that means that we're going to plug 10 into the derivative, which would be 3 minus 1200 times 10 to the negative 2. So I'll use Excel, and when we get to Excel, I'll interpret that. Okay, this next one just wants you to find the IRC when s is 10. So my input is speed in knots. My output is cost, and I want to just evaluate the derivative at 10. And I've already taken this derivative here. So that's equals 3 minus 1200 times a2 to the negative 2. So this is an instantaneous rate of change. Let me make sure I put it in right. Okay, and so this time it's a negative 9. So to interpret this, we know that the units are going to be dollars per additional knot. So to interpret the IRC at 10, when s is 10, 10 is speed, so at 10 knots, the function is a cost of fuel. So the cost of fuel is, this time it's a negative IRC, so it would be, is decreasing at a rate of, now you take the negative off because you wrote decreasing, so it's just going to be 9, and the units are dollars, so $9 per additional knot. Number 5 says a company's total annual cost in millions of dollars is given by the function c of t equals 100 minus 50 divided by e to the t, where t is time and the units are years. So my input is time in years. And c, my output, is cost in millions of dollars. And we are asked to find and interpret c prime of t. So we need to find this derivative. And so we have 50 divided by e of t here. So I'm going to rewrite this as c of t equals 100 minus 50 e to the negative t. So that's not a derivative, that's just a rewrite. And I'm going to put a negative 1 here because this is a little tricky. The derivative of this, well, the derivative of 100 is 0. So basically we just need to take this derivative. And this is the chain rule for e to the x functions. So the way you do that is, remember, the derivative of negative 50e to the negative 1t is negative 50e to the negative 1t. But then you have to take the derivative of this power here, which is negative 1. So if we simplify this, negative 50 times negative 1 is positive 50e to the negative t. So that's the derivative, and then you want to find c prime of 3. So that's going to look like 50e to the negative 3, and we'll use Excel to give us that answer, and then we'll interpret it. Okay, so this one we're asked to find c prime of 3, which means you had to take the derivative, which we did, and evaluate at 3. So my input is t for time in years. My output is cost, but it's money in millions, and we're trying to find the derivative. So we want to go ahead and put the 3 in, and let's put this derivative in, which is right here. And I went ahead and plugged the -3 in if we were showing our work. I'm just going to put in 50 times, remember E, do EXP, no caret, just parentheses, negative, understood 1 times A2. And so I would write that value right here equals 2.48935. And so now it's time to interpret. So we got to make sure we're good with these units. This is the math numbers. This is time in years, 3 years. This is cost in millions. So let's go ahead and take this and multiply by 1,000,000. So we have that value. So now we can interpret. The instantaneous rate of change would be at 3 years. The function is company's total annual cost. The total annual cost is, it's positive, increasing at a rate of, we could say this 2.49 million, or we could use this already multiplied out value. So I'm going to use the multiplied out value. So it's increasing at a rate of 248,935,3, and I'm going to put my commas in. So I can now see it's $2,489,353 per year. So you could use that interpretation, or if you look at the key, I just wrote at 3 years the cost is increasing at a rate of $2.49 million per year. So either one is okay. Okay, IRC number 6 says you deposit $1,000 in an account with an annual interest rate of R compounded monthly. At the end of 5 years, the balance can be computed using the following formula. You can figure out your final amount because it equals 1,000 times 1 plus R over 12 to the 60. So if you know the interest rate, you'll know the final amount. So my input is R, which is the interest rate, and then my output is A, which is the final amount, and that's in dollars. And it says find dA slash dr, which is the derivative of A with respect to R, for the following rates, and interpret each result. So we'll plug this in, but first we need to find this derivative. So this function, the derivative of this function would be A prime of R. And this, you're going to need to use the chain rule here because you have a binomial to a power. So the chain rule is you treat this like just a big variable, 1,000 times x to the 60th, for example. So this is going to be 1,000. You can bring that constant straight down. And then take the derivative of this. We call it the derivative of the outside. So that would be 60 times 1 plus R over 12 unchanged to the 59 power. And then the chain rule says after you take the derivative of the outside, you take the derivative of the inside. So what's going on here is that this R over 12 is really 1/12 times R. So if we want to take this derivative, the derivative of 1 is 0, and the derivative of 1/12 R is simply 1/12. So let's look at it again. 1,000 is your constant, comes on down. This, we're going to use a chain rule. It would be 60 times 1 plus R over 12 to the 59, and then times the derivative of the inside, which is just 1/12. So we have now the derivative, and we're going to now plug these in. And remember, if we're going to use this formula here, the percentage has to be changed to a decimal. So we're going to evaluate 0.08, 0.1, and 0.12, and we'll use Excel to do that. Okay, so this last one I'm going to do with you, it asks for the derivative of A and interpret each of these values. So I found the IRC. My input is R, which is interest rate as a decimal. My output is A, which is the amount of money. And I want to evaluate when R is 0.08, 0.1, and 0.12. So I'll go ahead and put those values in. And I want to find the derivative, which is the instantaneous rate of change, which I found right here. So that's 1,000 times 60 times parentheses 1 plus R divided by 12, close parentheses, caret 59, times the derivative of the inside was 1/12, 1 over 12. Let's see if we can check it before we hit enter. That looks good. So then if we drag it down, we have these three IRCs, and I think I have the key. I'll go ahead and go over there and you can see. Let's make it bigger. Let's make sure we have the same values. I did find both of, I found the original and the IRC. So just to practice, this here is saying that the amount at 8% at the end of 5 years is $1,489.85. That's like an if then. If you got an 8% interest rate, then that's your amount. But the IRC gives you something different, and so here are the interpretations for this one in blue here. At 8%, at an 8% interest rate, the amount or the balance is increasing at a rate of $7,399.90 per additional interest rate increase. You can leave that word off, but remember, it's always the units are always Y units, which is dollars, per X unit, and R is interest rate. And so in each additional interest rate increase is going to cause that. So the second one right here, at a 10% interest rate, the balance is increasing at $8,158.50 per additional interest rate increase, per 1% interest rate increase. And then the last one, at 12%, at that 12% interest rate, at that instant, the balance is increasing at $8,933.55 per 1% interest rate increase. So this is a little bit tricky. This is a decimal, and so every time you increase the interest rate, it's going to increase the amount at that rate. That's the rate of increase.